Every single time you send an email, stream a movie, or even just browse a web page, you're actually relying on a set of invisible rules. Rules that were written all the way back in 1981. They're the secret language of the internet, and today we're going to decode them. And it all starts with this fundamental paradox right at the heart of our digital world.
So here's the thing that's kind of wild when you think about it. On one hand, the actual nuts and bolts of the internet, the raw network, is a chaotic, unreliable mess. I mean, it's designed to be simple, which also means it's just not trustworthy. But on the other hand, what you and I experience is smooth, it's orderly, it's reliable. You can download a huge file, and it just works perfectly every single time.
So what's the magic trick here? What happens in between that chaos and the order we see on our screens? Well, it's not really magic at all. It's just a brilliant piece of engineering called the Transmission Control Protocol, or TCP. And in this explainer, we're going to pull back the curtain and see exactly how it works.
To really get TCP, you first have to understand the problem it was built to solve. So imagine you want to send a really long letter, like a whole book. The internet can't just mail that in one giant envelope, no way. Instead, it has to chop your book up into thousands of tiny little pieces, kind of like sending it one postcard at a time.
Now, the basic mail service for these postcards is called the Internet Protocol, or IP. And you should think of IP as a postman who, tries his best, but he makes absolutely zero guarantees. Seriously, he might lose a few of your postcards, he might deliver them completely out of order, or he could even accidentally give you the same postcard twice. This is the messy, unreliable system that TCP has to build on top of. And here is that chaos in action. Let's say we send 5 perfectly numbered postcards out into the network. But what actually arrives on the other side is, well, it's a jumble. You get postcard number 1, then number 4, then number 2. And what about postcards 3 and 5? Poof, they're just gone, lost somewhere in the digital void. Without some rules to fix this, our message is basically unreadable garbage.
And this is where our hero, TCP, enters the story. First laid out in a 1981 document. Get this, it's called RFC 793. TCP is a protocol. It's just a shared set of rules that both the sender and the receiver agree to follow. It's like a contract that's specifically designed to create perfect reliability out of that totally unreliable postcard service. So how does it all kick off? Well, before a single postcard gets sent, the two computers have to formally introduce themselves and agree to talk. And this isn't just some casual hey. It's a very specific 3-step process we call the 3-way handshake. It's really just like a polite phone call. The first computer sends a little message with a SYN flag, that's short for synchronize. It's basically asking, hey, can we talk? The second computer replies with something called a SYN-ACK, which means, yep, I hear you and I'd like to talk too. Finally, the first computer sends back one last ACK, or acknowledgement, saying, awesome, I heard you, we're connected. Only after this little dance is complete can the actual data start to flow.
Okay, so the connection is open, we have a line, but we still have that big problem of jumbled and missing postcards, right? So how does TCP solve that? Well, the solution is it's so elegant and incredibly detailed.
The first piece of TCP's genius is something called the sequence number. And get this, it doesn't just number each postcard or packet. No, it numbers every single byte of data being sent. It's this obsessive, meticulous numbering that lets the computer on the other end know the exact order of every single piece of the puzzle, no matter what crazy order the postcards happen to arrive in.
And this numbering system works hand in hand with another crucial trick. As the receiver gets the postcards, it's constantly sending back these little acknowledgments, or ACKs. But it doesn't just say, hey, I got postcard number 4. It's smarter than that. It says, I have received everything perfectly up to postcard number 5. So if the sender doesn't get an ACK for postcard number 3 after a little while, it just assumes it got lost and sends it again. It's a simple idea that makes sure nothing is ever lost for good.
So we've solved for lost and out-of-order data. That's huge. But there's another potential problem. What if the sender is really fast and the receiver is maybe a little slow? How do we stop the sender from just overwhelming the receiver with a massive flood of postcards?
Well, TCP has this built-in politeness protocol for exactly this situation. It's called flow control. And it's basically a system that lets the receiver, not the sender, be the one to set the pace of the entire conversation.
So here's how it works. With every single acknowledgement it sends back, the receiver also includes a little number called the receive window. This number is a message to the sender that says, okay, right now I have enough memory to handle exactly 4 more of your postcards. Don't you dare send me more than that until you hear from me again. This window size can get bigger or smaller on the fly, making sure the receiver never gets buried in data. All right, we've set up a connection, we sent our data reliably, and we've even managed the speed. But what about ending the conversation? You can't just hang up, right? A clean, graceful goodbye is just as important to make sure no final pieces of data get lost right at the end.
So, the goodbye is actually a four-step process. First, one side sends a fin flag for finish, which says, "I'm all done sending things to you." The other side acknowledges that, saying, "Okay, got it." Then, when that side is also ready to close up shop, it sends its own fin flag. The first side sends one final acknowledgement, and only then is the connection officially and cleanly closed.
So we've covered the technical nuts and bolts of TCP, but the original designers actually embedded something, well, more profound into its DNA, a core philosophy that has really guided how the entire internet has been built ever since.
You see, that original 1981 document, RFC 793, isn't just a bunch of dry technical specs. Buried inside its pages is this surprisingly human piece of wisdom that explains why the internet is as resilient as it is.
It's called the robustness principle, and here it is. Be conservative in what you do, be liberal in what you accept from others. The idea is just so simple and powerful. It means you should be extremely strict and careful about the data you sent out, follow the rules perfectly. But you should be tolerant and flexible about what you receive from others, trying your best to understand their data even if it's not quite perfect. This one sentence is basically the internet's golden rule. So let's just recap the whole thing. TCP takes this fundamentally chaotic, unreliable network and builds a rock-solid, reliable service right on top of it. It uses a formal handshake to start things off, sequence numbers and acknowledgments to guarantee delivery and order, flow control to manage the pace, and the whole thing is guided by this amazing philosophy of being robust. This is the invisible engine that truly makes our digital world possible.
TCP is just one of these hidden systems. And it kind of makes you wonder, right? What other invisible protocols and unspoken rules are quietly running in the background, shaping our economy, our society, our daily lives, turning chaos into predictable, reliable order? Definitely something to think about. Thanks for tuning in.